Welcome to Intelligent Systems, an introduction to artificial intelligence. In today's video, we will look into how to use probabilistic reasoning with a Bayes theorem in order to make predictions, and we will apply this specifically to the problem of spam classification. So given a message that contains the word congratulations, how likely is it that this message is spam? So we can express this as a conditional probability where, given the word congratulations, what is the likelihood that the message is spam? And by the definition of conditional probabilities, we can change that into this formula. Given the word spam, what is the likelihood of the word congratulations times the probability of having a spam message divided by the probability of having congratulations in any message. Now, the same thing can be computed for the ham messages, and then we can relate them to each other. So we can ask, given congratulations, is spam more likely or ham more likely? And by their definitions, we see that the likelihood of having congratulation cancels each other out if we view this as a ratio, and that means ultimately, in order to answer this question, we simply have to calculate the likelihood of congratulation given a spam message times the likelihood of spam and something similar for ham. Whichever of these two is greater, that's our prediction. So that's in a nutshell what we're going to implement, and we will see on a benchmark data set how good this method will perform. But before we do so, let's dig deeper into the details and the background of the Bayes theorem and how to make use of it for such a classification system. So in probability theory, we have experiments with results x1 to xn. And we have relative frequencies of these events when they're repeated often that vary between 0 and 1. So for example, that we have caries in our teeth, that likelihood could be 10%. So the conditional probability is stating that we find A and B to be true given the likelihood of B. So A and B happen in relation to the probability that B happens. So if we view this in these diagrams, then we have here the events A, the events B, the intersection, so A and B are both happening in relation to B happening. Now, this must be distinguished from an if, and in practice you should also say for the conditional probability A given B rather than A if B, although in practice this is done differently often, sometimes. Okay, so if we look at the implication, then it covers both cases where B has happened and where it has not happened, whereas the conditional probability only considers the case that B has happened already. So the conditional probability relates this circle to this, whereas the if statement relates the entirety to this. And how does the implication do that? So let's see what formally A and B implies A if B, what that means. By logic, we can specify this also as A or not B, and this is equivalent to A and B, or A and not B, or not A, not B. So essentially, we have A not B over here, we have A and B over here, and we have not A and not B over here. So we exclude essentially everything but this part. Now, those probabilities are really different, and let's just take a quick example to demonstrate that also concretely. So let's assume that A and B both happen with 50%. And let's say that A and B together happen with a likelihood of 25%. A and not B happens with 25%, not A, B happens with 25%, and that both of them are not happening has a likelihood of 25%. Now, let's plug these values into the definitions of a conditional probability and to A if B, and let's see what is happening. So A and B has the likelihood of 25%, that's this part over here, divided by the likelihood of B. And B taken together is 50%. So 25% divided by 50% is 50% in total. In contrast, our implication is the sum of this likelihood, and this likelihood. And that's 3 times 25%, overall 75%. So if and conditional probability are really two different things. Now, when we're having more than one variable, we can look at joint probability distributions. So consider the case of two variables, and with their atomic events, with the outcome values for these variables. And let's consider concretely the case of pain and carriers. And pain can be there or it can be absent. Carriers can be there or they can be absent. And here we have the probabilities. So pain and carriers comes with 4% likelihood. No pain, no carriers comes with 89%. And overall, these four probabilities sum up to 1. And we can actually add these probabilities. So the likelihood of carriers is 0.04 plus 0.06, so 10%. The likelihood of carriers or pain is basically this value, that value, and this value. So that will be 11%. And the likelihood of carriers given pain is carriers and pain divided by the likelihood of pain. So that means 0.04 divided by 0.04 plus 0.01, 0.05, that's 80% in total. So the likelihood that we have carriers given pain is actually quite high, although the likelihood of carriers in general was only 4% and here 6%. And the reason is, of course, that we relate the case of pain and carriers to the situation where pain is present, which is only in 5% of the cases. So now let's play a little bit with the definition of a conditional probability. So in the previous slide, we defined that A given B, or the likelihood of A given B, is equal to the likelihood of A and B divided by the likelihood of PB. Now, if we multiply this equation by PB, then we get this equation over here. So we have related A and B to the conditional probability of A given B times probability of B. We can do the same the other way around for the conditional probability of B given A, and then we have two different definitions of the likelihood of A and B. Now, we can equate those two because they are the same over here, and then we get conditional probability of A given B times probability of B is equal to conditional probability of B given A times probability of A. Now, let's just divide this now again by PB, and then we have Bayes' rules. So Bayes' rules gives us a definition of this conditional probability A given B in terms of probability of B given A times probability of A divided by probability of B. Now, this is important because using the joint probability distributions of the previous slides has the problem of a combinatorial explosion as we're creating more and more variables. And we will see, specifically in our span problem, that we will need many variables because in the span situation, we have, for example, many pieces of evidence like the word congratulations, the word your, the word okay, the word winning, etc. All of these words appearing in the message. They're independent pieces of evidence that we have to relate to the event it's a spam message or it's a ham message. And that means in order to practically use the Bayes theorem, we will always deal with many variables. And that means that the joint probability distribution is not a viable approach, but instead we have this formula here, which we will see we can extend that it also handles multiple pieces of evidence, B1, B2, B3. But let's do this step by step. So first of all, the big question is, okay, now that we have the Bayes formula, well, is it actually easy to compute all of these three probabilities over here or not? And specifically, of course, we cannot answer that in general for any situation, but we'll look into a specific setup, a medical example where we have symptoms and we want to conclude from given symptoms to a diagnosis, and that will allow us to determine what is easy and what is maybe more difficult to calculate here. Well, we will actually find that PB is difficult to compute, and then we wonder whether we can actually get some information about this conditional probability without PB. Of course, we cannot change the formula, but we will see that we can change the task, and we will see that instead of computing the exact value of A given B, we calculate it in relation to another A prime given B. And then we just answer whether this is more likely or that. We will also see that we can maybe reformulate PB in a different manner where we have information on the event that A is not happening, and that helps us maybe to calculate PB implicitly. And finally, we extend our basic setup of A given B into A given B1, B2, and so on. So let's iterate through these different aspects of the Bayes theorem one by one. And let's start with our setup of a medical example. But this is a very high-level example that can be basically rolled out to many, many different scenarios. And essentially, it's just that we have a symptom and we want to diagnose a disease. And it can be that we have some evidence and we want to have some conclusion. Evidence like a certain word appearing in a message, and we want to draw the conclusion it's spam. Or evidence of a shape of a fruit, that it's round and has a smooth surface and has the color green, and we want to draw a conclusion on whether it's an apple or an orange. So therefore, this setup is general. But let's look at it specifically here. Meningitis, the diagnosis, goes together with symptoms of, for example, a stiff neck. And actually, when you have a meningitis, it's quite likely that you have a stiff neck, namely in 50% of the cases. Fortunately, meningitis, it's an inflammation in the brain and it's a pretty severe disease, is not that likely, so it has an incidence of 1 in 50,000. In contrast, the stiff neck has a much higher incidence, 1 in 20. Now, we're in a scenario where a patient comes to a doctor and says, I've got a stiff neck, and the doctor wants to assess, now what's the likelihood of this being a symptom for a meningitis? So we want to have the conditional probability that given we have observed a stiff neck, what is the likelihood that the correct diagnosis is meningitis? And through the Bayes theorem, we can turn this into the likelihood of observing a stiff neck given that we know it's a meningitis, times the probability of having a meningitis divided by the probability of having a stiff neck. Now for our setup, we have all these three numbers given. The conditional probability was 50%. The incidence for the meningitis was 1 in 50,000, and for the stiff neck, 1 in 20. And if you throw these values together, you get 0.0002. So the likelihood of the meningitis is actually not really that high. So fine, we have those three values given, and that means we could calculate our conditional probability that we wanted. But in practice, how easy or difficult is it to actually obtain the data that we need for this calculation? So let's look first of all at the likelihood of a meningitis and the likelihood of a stiff neck given a meningitis. That is actually not that difficult to get by because it's safe to assume that a meningitis is so severe that patients would seek a treatment with a doctor. And that means in order to obtain this data, we could work together with doctors. They could collect this data and they could give us the probabilities of the meningitis and how frequently they observe stiff necks with a meningitis. In contrast, the other probabilities, the stiff neck and a meningitis being observed when there is a stiff neck, is much more difficult to get by. To have knowledge about meningitis, about stiff necks in general, we would have to ask the whole population, because there will be many people who would not go with a stiff neck to the doctor, right? And so asking the doctors is not sufficient. It will escape. Many people will not be present in our count. And so the same actually applies then for the people with stiff neck, so given stiff neck and meningitis. So those two values are difficult to obtain. Well, it's not that bad, these two easy. This was actually what we wanted to calculate in the first place from those three. So actually the only tricky bit we have to deal with is difficult to get the likelihood of the stiff necks. Yeah, so we have summarized this to see again. So could it be a meningitis? We can answer this if we have those three values given, because that's the question we try to answer. And question is, are they easy to obtain? And answer is those two, yep, we can get them. That one is a tricky one. And now we say, okay, we cannot change the formula, but is there maybe a way how we can get rid of P of S? And the answer is yes, there is, because we change the task. We don't change the equation. And we make it a relative question. So instead of asking what is the exact probability of the diagnosis meningitis given a stiff neck, we just want to know what is more likely, a diagnosis of meningitis or a diagnosis of an injury that actually led to the stiff neck. And as we're asking this relative question, we will see that P of S cancels out and we don't have to calculate it at all. So let's now relate these two conditional probabilities, and our injury is called W. And we built this fraction. So given a stiff neck, what is the likelihood of meningitis? Given a stiff neck, what is the likelihood of an injury? Divide those two probabilities and then make your decision. So let's assume that a stiff neck is quite common with a meningitis, 50%, but actually it's even more common with an injury, 80%. The meningitis was 1 in 50,000. Injury, let's say, is 1 in 1,000. So again, it's a much more frequent complaint. Now, we have all of the numbers together, and that means we can calculate this ratio without using the probability of a stiff neck, which we said was difficult to calculate. Sticking in all of these values, we get a ratio of 1 to 80. So that means it's much more likely that the correct diagnosis is injury than meningitis. So quite a good outcome. Now, that was the first aspect. We changed the task in order to get rid of a probability that is practically sometimes difficult to calculate. Let's take another approach. That probability that is so difficult can be also written down by the very definition of conditional probabilities as follows. Namely, we can break down the case where we do have a meningitis and the case where we don't have a meningitis. So this probability is equal to a stiff neck given meningitis times the likelihood of meningitis, plus the probability of a stiff neck and there is no meningitis times the probability that there is no meningitis. Now you will say, well, but look, that was difficult, and if we could get that, that is also difficult, isn't it? But we argued that this part is easier to obtain, and let's just say we have it, and let's say by some magic there was also a way how we could maybe estimate these values over here, or we have a special setup where we can get those values, right? So for this case of meningitis, this is maybe not so true, but for other scenarios, there might be a different source how to obtain this conditional probability and this probability. And then we have a good estimate for this, and then it means we can calculate this probability here, and instead of using P of S, we use this instead. So that's the second way how to implicitly get rid of P of S. Now, the third aspect in the base rule was that we wanted to deal with multiple pieces of evidence, and that was evident in this medical scenario where typically a patient will not just have one symptom, but there will be multiple symptoms. It's of course the same when we're looking at messages where a word being part of a message and we have multiple words in the message, so multiple pieces of evidence. So let's take the basic rule. over here, and now we simply plug in two pieces of evidence for B. So instead of having B, we have B and C. So over here, B, C, B, C, B, C. So that's easy. We can just do that. Now, the big question is how can we simplify that? And there we can make an assumption. We can say that B and C are independent of each other, and then we can change this formula into this one, and this conditional probability becomes these simpler two conditional probabilities, namely given A, the likelihood of B, given A, the likelihood of C, multiply those two, rest stays the same. Now, how valid is this assumption that B and C are independent? Generally, there will be many cases where it is, but practically, of course, there will be exceptions. So take, for example, words and messages. Are they always independent of each other? Well, usually, maybe yes. The word ball and the word key are not dependent on each other. But I am, those two words, they are kind of dependent of each other. The same for symptoms. A stiff neck and a stiff shoulder, well, that's, I guess, not that likely that's completely independent. But, I don't know, a stiff neck and, I don't know, a headache, that could be completely independent. So anyway, we're making this assumption, but we have to be aware that there will be actually cases where it's not valid to do so. But if we can, then our scenario, our classification scenario, where we want to distinguish A1 and A2, it turns into this calculation that we can basically assume A1 to happen, and we check probability of B of C, multiply that by the probability of A1, do the same for A2, and that's our decision criterion, where, for example, A1 is ham and A2 is spam, and these pieces of evidence are the word congratulation in the message or winning or something in the message. Now, let's apply this practically. And for a simple scenario where we collected data, we have apples, oranges, and bananas, and we had 1,000 cases, 400 apples, 300 oranges, 300 bananas. We had three attributes. Is it round? Is it smooth? Is it red? And now the 400 apples, 90% were round, 80% were smooth, had a smooth surface, and 60% were red. Note these probabilities don't add up, and these probabilities only apply to apples, those only to oranges, and those only to bananas. So this is not a joint probability distribution as we've seen it in the previous slide. And our question is, what is this fruit over here? Practically, that means we want to compute the conditional probability of an apple given that the fruit is round, has a smooth surface, and is not red. The same for orange and banana. Now, let's abbreviate that a little bit. A, apple becomes A, orange O, B for banana, round for R, smooth for S, or S for smooth, and not red is so short that we keep it. So that's what we want to calculate. And this amounts to the likelihood of R given A, S given A, not red given A, times the likelihood of A. Now, I put here a tilde because this is not an equal, because what I dropped was the divided by, and in the denominator there should have been PR times PS times P not red, if we wanted to have the equal symbol. But since all of these three conditional probabilities have the same denominator, I removed the denominator and put the tilde symbol here instead of the equal symbol. Now moving on, here we can put the equal symbol because we just inserted the values from the table. So round given apple is this 90%, see it over here. Smooth surface given apple is 80%, so that's 80% over there. Not red given apple, so red is 60%, that means not red is 40%, and that's those 40%. And this 40% is something different. We had 400 apples out of 1,000 fruit in total, so it means 40%. We do the same for the other fruit too, and that gives us 12%, 6%, 2%, and that means from applying the base rule to our data setup, we can infer the fruit that we're seeing here is an apple. Now, let's turn to a really proper practical application and build a spam filter using the base rule. And a little digression, spam is actually what you see depicted here. So spam was a food that was sold in Britain after the war when food was scarce, and it was some mashed up meat, and supposedly it stands for salted pork and meat, and it was apparently not very tasty. People didn't really like it. And the comedy group Monty Python, who by the way gave rise to the programming language Python, so Python, the language you're using, takes its name from the comedy group Monty Python. I think you should know that. So those people were pretty influential. And were also influential on spam messages, because they basically had a sketch in which somebody wants to order a typical English breakfast, as you know, which consists out of beans and bacon and a fried egg and a toast and some marmalade and mushrooms and fried tomatoes. So that's a typical English breakfast. And in that sketch, the menu offers egg and bacon, egg sausage and bacon, egg and spam, egg bacon and spam, egg bacon sausage and spam, egg bacon sausage and spam, spam egg spam, spam bacon and spam spam egg spam. It's pretty hilarious, although it's pretty outdated too. And I just wanted to play with the fact that everybody hated spam, and nonetheless spam found its way on the menu. And as a result, spam was actually a good name for those messages that you don't really want to get, but nonetheless you get them over and over again. So anyway, end of digression. So that's the reason why we have spam messages and why they're called spam. And with the data set that we have at hand, the first thing we do, as in any machine learning and any data science, is let's get familiar with that data set. And that's really an important step. We want to look at many of the messages. We want to develop an intuition of the messages. We want to see some obvious things visually, where we can say already, oh, that looks strange, or that looks specific to ham or spam. Then we prepare our data so that we can process it. And that means we have to turn strings into vectors. And I mention it here. We will have in our setup a trivial solution to that. But I mention it here because we will come back to that issue when we do more text processing and natural language processing. Then we finally apply the base rule, as you've seen it before, to decide, is it more likely, given a message, that it's ham or spam? And finally, we tackle two problems that we encounter during this process, namely, what if a word is not in the training data? And this thing that we discussed already, are all of the words independent of each other or not, and how to handle this. So here's the data set. It contains 4,459 messages, 86% are ham, 13% are spam. So that means automatically our baseline is we want to be way better than 86% in our classification, because a trivial classification would always just say it's ham and we're done and we do already 80% correct. And here are just some random examples. So that's the first step in any data processing that you do. Write a tiny program that shows you random samples from your data and look at them. So if you have 5,000 messages, you should have looked at least at 500 of those messages. So here we have just a handful, and you see already spam. Congratulations, you're awarded 500 off CD voucher, and you immediately, as a human, you observe this is not correct English, or 125 gift guaranteed. This looks weird. Whereas, for example, the message above, well, good morning, Mr. How's London, treating you treacle. That looks not so, that doesn't look so bad. So develop an intuition, and you will immediately come up yourself with ideas of how you would actually, as a human, run that classification. So one thing that I did when I looked at this, I said, okay, what are the shortest and longest messages besides the random ones? So think of just some criterion how you could sort the messages and look at the average one, look at the extreme ones. And actually what you find is the shortest messages are okay, yep, okay dot, okay comma, smiley, okay dot dot, okay dot dot dot, you too. Oh, that's quite interesting. And surprisingly, all of the short messages are ham messages. And that's actually interesting already. That's an interesting finding that, of course, a spam message cannot be 2 characters long because they want to sell you something, they want you to answer, etc. Whereas a ham message is sometimes, or actually pretty often, it will be part of a conversation. The message okay only makes sense if a conversation took place, and if I ask something, or that other person asks something, and I say, yeah, fine, okay, only then it makes sense, right? Whereas a spam message will typically be on its own. So that's already an interesting finding that very short messages tend to be a ham. But how about very long messages? Actually, the longest I found was this one. For me, the love should start with attraction. I should feel that I need her every time around me. She should be the first thing which comes to my thoughts. Interesting question, romantic, very, very long. It actually goes on and on for quite a bit. And there I would also say, if you just show that to me without telling me whether it's ham or spam, sentences are well formed, grammar is fine, the contents is fine, reasonable reasoning, that looks to me like ham. And in fact, it is ham. And now when you plot this properly, you will actually find that the spam messages, they all center around 150 characters, whereas the ham messages, they tend to be much shorter on average, but you also find a couple of really, really long ones. Yeah, so length is a big difference between ham and spam. Interesting. Yeah, and you just find that by looking at some of the messages, formulating a hypothesis, and then playing around with the data, writing a short Python script, and doing something with it. So yeah. Anyway, when I saw okay is a frequent ham message, then I thought, well, or is a ham message, then I thought, well, okay, will actually be pretty frequent. How frequent will it actually be? If half of this of these several thousand messages are okay, then a data set is pretty pointless, right? And there's a danger of overfitting because I just learn the rule, is the message okay? Then I say ham, and otherwise I say it's spam. So next thing I did was count the frequent messages, or how frequent they are. And actually the most frequent with 30 occurrences is sorry, I'll call later. Well, that is probably a predefined message that you can automatically send. You get a call that you cannot take, and a button offers to automatically send that message to the caller because you're in a meeting or something. Then 10 times okay and 3 dots, 4 times okay dot, 4 times okay. If we do this count properly, we should probably aggregate okay 3 dots, okay 1 dot, okay 2 dots, okay blah blah blah. And then you would see that somehow okay agreeing is the most frequent message. So anyway, most of the frequent messages are ham, but we also find here a spam message that appears 4 times. Please call our customer service representative on free phone, blah, blah, blah. And then it says, you have won a guaranteed 1,000 cash or 5,000 pound prize. Yeah, and again, yeah, interesting. But a second criterion, besides length, frequency of the message, is apparently a good indicator for ham. I would not have thought so before, because I would have thought that spam messages are repetitive and over and over again the same message gets sent. But anyway, in our data set, that's not the case. So be that as it may, so I developed through this a bit of an intuition of the data, but our goal was we wanted to analyze the contents of the messages and from that make a prediction with the Bayes theorem on whether it's spam or it's ham. So let's actually do this, and let's analyze those words in the messages. And we have in those messages, in in the spam message is 13,000 words, or nearly 14,000. In ham, it's nearly 8,000. And in common, they have nearly 6,000 words. And when you compare the frequent words in spam and ham, there's a lot of agreement. So you can see here the most frequent ones in spam, most frequent ones in ham. And if you look, the frequent words common to both are to, you, I, a, the, in, and, is, I, for, my, of, you, me, your, have, on, that, are, or, and so on. These are actually called stop words, and they're highly frequent. In fact, in Google, you cannot search for the word I, because nearly every document will contain the word I. And those are not very informative. You could exclude these words right from the start from all of your analysis. You wouldn't lose much. Now, let's look at words that are only in spam, 2,000 of them, and look for frequent ones. That's already more interesting. One, TNC, representative, weekly, SMI, Word, Bluetooth, Dell. Same for ham. That's, yeah, change, back, her, second, worry, seeing, swing, wish, crave. You see, very different. You see also right away, dot over here. We probably should do a bit more cleaning when we obtain our words, that we get rid of these delimiters like dots, or here like the asterisk and grin. But you see already the frequent ham words have a different feel to them than the spam words with one and Bluetooth. But you also see already that here we have maybe a likelihood of overfitting. T and C, that doesn't look like, although it was pretty frequent, that it generalizes quite a bit, whereas one, or capital, that probably does generalize quite well. So, anyway, yeah, and by the way, to get this analysis of frequent words in ham and spam, we had to carry out step 2 already. We're now here still at step 1, which was turn the string into words. We did actually something super simple. We just applied to the message string the Python command split that splits the string at white spaces. So that means a new line and add a space. So therefore, here comes step 2, properly prepare the data, move from a string to a vector, tokenization. And as I said, we applied something very simple here, but in general, this is actually a hard question. This is not so easy to do. What is actually a token? Is it a character, as we have considered, or that would be a low-level characterization, as we have done here, or is it a word? What is actually a word? Do we include stuff like the dots in the word? Do we scrape those dots in OK, ... entirely? We may lose information. What if you have words that have a hyphen? Information, space processing, information, dash processing. Is that one word, or are these two words? So determining the boundaries of a word is actually not that trivial. So something in between. And in fact, in neural networks, and especially in really big ones like ChatGPT, you do actually apply something that is sitting in between characters and words. And the motivation is you don't want to lose the information of words and the units of words, and at the same time you don't want to have characters because they're not so meaningful, but something in between. And you want to be as compact as is possible because you have so large amounts of data. You want a representation that is better than just looking at the characters individually. And so what is done in data preparation for neural networks, that you change your strings from a character representation into your own encoding. And one typical example that is also used in compression algorithms is called byte pair encoding. And what you just do is, starting from single characters, you say which are the two most frequent single characters, and you say, okay, for those two, if they come next to each other, I introduce a new code. I introduce a new artificial encoding. And then basically I replace all of the occurrences where these two most frequent characters appear next to each other by this new code that I have. And then I iterate this process over and over again until I have introduced or until I have used up all of the codes that were provided. So I say, for example, I define a size of 100, and let's say 26 letters for the standard letters, lowercase and uppercase, so add the digits to it, and that leaves me a small part of characters which I can use for this byte encoding. Or maybe increase it to 500 to dig more. And what will this do? So this byte encoding, it should definitely find things like ing in English. Byte pair encoding. The ending ing is very, very frequent. So the byte pair encoding should actually introduce a new code for the three letters ing next to each other. That will make the overall data that I need, the overall space that I need to represent the data, probably much more compact. So this just as a little shout out for neural networks where it really matters. It's quite interesting. You actually take an encoding that is sitting somewhere between characters. It has aspects of characters, but it also has aspects of words. For our case, as I said, we just do something very, very simple. And we just say we deal with kind of words which arise from splitting at space and new line and stuff. Okay, so with that, we can come to step 3, and that is we apply finally the base rule with the multiple pieces of evidence. So we have to calculate that the likelihood of a piece of evidence, the likelihood of piece of evidence B and C given for ham, and the likelihood B and C given for spam. And we turn this into the likelihood that A1 is given, and so we know it's ham, and we observed the word congratulations. We know it's ham, and we observed the word awarded times the likelihood of ham, and so on. So we apply this formula as we introduced it. So this breaks down to this calculation over here, and we ask, is this side bigger than that side? So the individual pieces of evidence, namely congratulations, you're awarded, and so on, multiplied in spam and given ham times the probability for spam, probability of ham, and depending which one is bigger, that's the one we want. Now, how difficult or easy are these likelihoods to calculate? Let's figure this out. Well, frequency of congratulations in spam message, well, that's easy. Just take all of the spam messages and count how frequent is congratulations. Normalize that by the amount of spam, and it gives you the probability. Frequency of your in spam, also easy. So all of these conditional probabilities are really easy to calculate for a data set. Probability of spam, well, that was also easy. We just count, I think 13% was spam and the rest was a ham. So those probabilities are also easy. So that means all of these numbers we have given, job done. We can simply apply the base rule and that way draw our conclusions. However, little caveat, before we come to the two problems that I mentioned in the introductory slides, one more slight tiny problem. What is actually the frequency of congratulations in spam messages? Do we count that on the message level? That we say if congratulations appears at least once in a message, then we count it. Or do we make a difference if it says congratulations, 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 that somehow this is weighted 3 times or something. So even for something simple as counting the frequency, you can basically define slight differences. And that's why I think it's quite nice that we can look at the code, because there we have homed in on really one specific interpretation of what frequency means here. So now let's turn to the problem. And in the introductory slide, I mentioned 2 problems. One, what if a word is not in the training set? And the second one, what if the words are not independent of each other? So what if a word is not in the training data? That is actually a really, really important problem, because we can guarantee that that will be the case. If we use our spam filter, we will encounter words we haven't seen before, because words get newly created. So that means our training data cannot be up to date with respect to all of the words that exist. Now, why is it such a problem if our test data does have a word that the training data did not have? Well, for that word, the likelihood of observing, for example, in spam, that word that was not seen in the training data, well, that conditional probability is 0. Now, and if that conditional probability is 0, well, then all of the conditional probabilities of both ham and spam, when basically going through evidence and it contains this 0 probability over here, then this automatically amounts to 0, because all of these individual conditional probabilities are multiplied with each other. So if one of them is 0, no matter how high or low the others are, everything turns out to be 0. So this 0 has a very, very big impact on the overall application. So we must get rid of that 0. How we do that? We simply replace that 0, which strictly speaking is true, by something that is very small. And that technique is called Laplace smoothing. So Laplace, the famous French mathematician. So the technique is called Laplace smoothing. And what we do specifically here is, instead of counting the spam messages with UR in it and the spam messages overall, we add here +1. So this here can never be 0. And we add here the size of the vocabulary. And that means even if that is 0 here, the whole denominator never becomes 0. And overall, we have ensured this can become very, very small, but it doesn't become 0. And we have avoided the propagation of that 0 despite the other values maybe being very high. So the second problem was that we assumed, when considering multiple pieces of evidence, that this evidence must be independent. Otherwise, we cannot turn to a multiplication of the conditional probabilities. Is that the case? And as I argued already, generally you can probably assume that, but always probably not. And specifically here in our messages, of course you do find frequent pairs: has been, I'll call, don't know, I'll text, day question mark, interesting, will be, don't think. These appear very, very frequently to each other, and this is basically a normalized value log-odds ratio between those two pairs. So they appear much more frequently than expected next to each other. So they're not independent of each other. How do we deal with that? Well, it's actually pretty easy. We just ignore it. We are aware of the problem, but we assume that only a minority of word pairs, a small minority of word pairs, will be dependent on each other, and the vast majority of word pairs will be independent of each other. And based on that assumption, we draw our inferences. And it's fine to do that, but we should be aware of that, and you should know the limits of your own approach. Now, that brings us to this piece of code. So this implements the full spam classifier using the base rule. And let's quickly go through this, explain a couple of lines. So we prepare our data here, we shuffle it, we break it down into training and test data, and we do so with a ratio of 80% training, 20% test. We extract the labels, we compute the probabilities of ham versus spam, and then we do the individual probabilities for all of the words after splitting all of the messages in ham or in spam. Yeah? So if the label was ham, then we increase the count of that word in the ham dictionary, otherwise it's in the spam dictionary, and that gives us the overall counts for a certain word within ham or within spam. The size of the vocabulary is defined over here, and that brings us already to the prediction that we can run. So that is the key piece of code. Just 2, 4, 6, 8 lines of code. So we initialize the conditional probability of our message being ham to 1.0 and spam 1.0, both equally likely at 1.0. And now iteratively we multiply this. And how do we multiply it? We take a word out, we take the likelihood that this word appears in ham, so that's the absolute count from the dictionary that we created here, plus 1 for Laplace smoothing, divided by the sum of all of the words in ham. That was what we calculated over here. So we normalized by the amount of messages, plus the size of the vocabulary. Yeah, so again, Laplace smoothing. Same for spam, and that means we really have here a normalized value. And then after multiplying all of these values from all of the words in the message, we finally multiply by the likelihood of having a ham message or a spam message. That's this final multiplication here, and whichever is greater is the one we pick, so either ham if it's greater or else spam. And then we run this for all of the test data, get the prediction, and then figure out whether we were true or whether our prediction was wrong, and from that we can calculate precision, recall, and accuracy. And you see over here 100% precision, recall 68%, overall an accuracy of 96%. So given that we're doing here something super simple, I would say that's actually not really too bad, and the overall amount of code is really, really short. And in fact, in early spam filtering, a Bayes theorem was really used in spam filters. So, more details on quantifying uncertainty you can find in Chapter 13 of Artificial Intelligence, A Modern Approach.